So, I will continue this lecture with the proof of this dimension formula. We have already proved this formula once before, but this time I will give a proof using rank theorem. So, proof. So, let me recall first, when you have two or many vector spaces, then we have considered their direct sum of vector spaces. So, first for arbitrary family, if Vi were vector spaces, k vector spaces, then the product set, on the product set, Cartesian product of Vi, we have a natural structure of addition, namely the component wise, and also component wise scalar multiplication. So, that make this Cartesian product as a k vector space. And I consider a subset of this, which is denoted by this direct plus circled plus. This is a subset of those I tuples Vi with the condition that almost all Vi's are 0. Vi equal to 0 for almost all I. This subset is called, and this subset is also clearly a subspace of this product space, because if you take two such tuples with this property that Vi's are almost all 0, then the sum will also have that property, scalar multiplication also will have that property. So, this is a k subspace of this product space, and this is called a direct sum of the family Vi. But in case of finite, if I were a finite index set, then obviously this subspace equal to the whole space. So, we are going to use it for two vector spaces, namely U and W. So, the direct sum U direct sum W is simply the direct product with a component wise structure, and obviously we have a natural map from U direct sum W to V. It is a very natural map. Also note that if U and W are finite dimensional, then this also finite dimensional. And a dimension of this will be equal to the sum of their dimensions. This is also very simple to prove. What one does is take a basis of U and take a basis of W and look at the new set, put first component the basis element of U and the second component 0 and the other way. So, what I am saying is the following: if Ui, I in I, basis of U, Wj, J in J, basis of W, then it is very easy to see that Ui comma 0 and 0 comma Wj, Ij varying, I is varying in, or I comma j varying in I cross j. This is a k basis of U cross W. This is very simple checking. In particular, dimension of the direct sum equal to sum of the dimensions. And now look at the map which is defined from U direct sum W to V. There is a natural map. So, the pair x comma y goes to x minus y. That is the definition of this map. So, let us call this map as F. So, what is easy to note is F is linear, F is K-linear. So, that means you will have to check the formula like F of A x y plus A prime x prime y prime. This should be equal to A f x y plus A prime f x prime y prime. But this is very easy to check because this definition here is component wise addition, component wise multiplication, and the f is simply taking the difference. So, this is just a rearrangement of vectors and scalars in the vector space. So, that shows that f is K-linear. Secondly, I want to say that the image of f is precisely the sum of u plus w. That means we need to check that image of f is the smallest subspace which contain u and it contain w also. But look here, if I take y equal to 0, then where this x is in u, y is in w. So, if I take y equal to 0, that is x is in u and that goes to x. So, therefore, clearly u is in the image, u is a subset of image. Similarly, w is a subset of image and it is the smallest one is apparently very easy to check. So, I will leave it to you. So, image is u plus w. Secondly, I want to compute the kernel. So, kernel f is all those pairs x comma y where it goes to 0. That means x minus y is 0. That means y is x. But that means kernel is precisely the diagonal x comma x where x varies in u. That is the kernel, obvious. And also note that this kernel is isomorphic to u as a vector space. Simply you can take x comma x map to x. This map is clearly linear and clearly bijective. Therefore, kernel of f is isomorphic to K vector space u. In particular, the dimensions are equal. So, therefore, when you apply rank theorem, what do we get? Rank theorem says this dimension equal to dimension of the image plus dimension of the kernel. So, let us write down the rank theorem. Okay. By rank theorem, dimension of the direct sum equal to dimension of the kernel plus dimension of the image. But we have just seen dimension of the kernel is precisely dimension of u. Oh, I made a little mistake. So, let me go back to the earlier page. Okay. So, kernel f, this is not isomorphic to u, but isomorphic to u intersection w. Because when we write x comma x, that is x is should be in u as well as x should be in w. So, this is really u intersection w, the map goes inside that, and which is clearly K linear and K isomorphism. So, going back, so this is kernel is the dimension of the intersection, and image we have checked that is nothing but the sum u plus w, and the other side we have just noted this is nothing but the sum of the dimensions. So it proves the formula what we want. This is the dimension formula. It is written, this side is written this side and this side is written that side, that is only difference. Okay. Okay. So one can also use this rank theorem to prove the one which theorem earlier, namely the map F on a finite dimensional vector space to finite dimensional vector space is an bijective map if and only if it is injective, for example. Injective is equivalent to saying kernel F is 0, but then that will mean that the image F will have the full dimension, but that will mean that it is surjective and therefore altogether bijective. So I will not write this explicitly here, but I would like to now discuss rank of a linear system. So the next example, rank of a system of linear equations. So once again, so start with the system of linear equations. I will let E be a system of m linear equations in n unknowns. Which we are calling it x1 to xn over a field K. So that means when we did Gauss elimination, that is how we were writing. Okay. So how were we writing? We were writing the first equation. The first index is for the equation. First equation number 1 1 x1 plus 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 a1 n xn equal to b1. This is the first equation. The first index of the coefficients ai's is the equation number. Second index is the variable number or unknown number. So and so on. So mth equation m1 x1 plus 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 a m n xn equal to bm, where all these a I j they are in k and b I are also in k, where I is the index 1 to m and j is the variable number 1 to n. So that is the data given to us, and we are looking for the solution space, that is x1 to xn in k power n. So this is how we are doing. So but instead of thinking like this, I want to consider, so instead make the notation also very compact and easier. Instead we consider the k linear map F, let us call it F, from the vector space k power n to the vector space k power m. So note this vector space is the space of all n tuples. with entries in K. This is a space of m tuples with entries in K. This has a basis, the standard basis is even to En. This also has a standard basis, but because we will get confused with which E where we are using, I will try to avoid using E's. Instead I will write n tuples and m tuples. So but I will need to use one of them at least. So I will say that E1 to En belong to Kn. This is standard K basis of Kn. I would also think them rather than rows, I would better think them as columns. Instead of writing E1 for example, instead of writing like this, n tuple like this, first entry is 1 and remaining entries are 0, that is the first basis element here. Instead of writing this, I would write it as 1 0 0. So this is instead of this is preferred. Okay. So that means I have give what is the linear map, and just remember that to give a linear map from a vector space, one vector space to the other vector space, I just have to give its values on a basis. So I just have to give you what is f of E1, f of En, and they should be an element, they should be vectors in K power m. That means they should be m tuples. So this one is what? Let us write down this. This one I want to call it Y1. This one I want to call it Yn. And what is Y1? Y1 is A1j, A2j, so on, Amj, m tuple. Either you write like this or like it as a column, and preference is write it as a column. Similarly, Yn is A n1, no, Ym, it should be the other way, sorry, this is correct, this is also the other way I wrote it, this is, there is no j here, sorry. So this, let us correct this. Y1 is A11, A21, AM1. Yn is A1n, A2n, Amn. These should be m tuples, so these are this one. So this is the first column. This is here, this one, this vector Y1 is nothing but this one. This is Y1. This is Yn. This is Y1 and this is Yn. Right. So that is how the linear map is defined. Then what do you do with this? Then what are we looking for? Then let us write down what are we looking for. Then we are looking for solutions. We are looking for tuples. Which tuples? X, let us call it X, which is x1 to xn in k power n, such that f of x equal to b. B is b1 to bn, b1 to bm. We are looking for this. So, given B, we are looking for all x with that this equation is satisfied. So, one can say that this is a linear system of equations. So, just f x equal to b for a given b, and now how to get x? Obviously, then the fiber over b is the solution space. Fiber over b, which is by definition all those x in k power n such that f of x equal to b, this is the solution space. Of f x equal to b. Okay. So, now I want to compute the rank of this linear map F. So, the rank of F, this is the dimension of the image space f of k power n. But the image space is generated by, this is k f of E1 plus k f of En. But this is f of E1, we have called it Y1. So, this is k Y1 plus k Yn. So, we want to compute this rank. So, this rank is also called the rank of the linear system. System E. And what is the solution? What is the corresponding homogeneous system? The corresponding homogeneous system. Remember that we have denoted by E0. That means in E, in the equations in E, we are putting B is 0. So, that is, and the solution space, the corresponding homogeneous system is denoted by this, and the solution space and its solution space we have denoted by L0, which is L0 is by definition L of E0. But what is this? This is nothing but now f inverse of 0, because we are taking b equal to 0, the fiber over 0, but this is nothing but the kernel of f. So, therefore dimension of the L0 is nothing but the dimension of the kernel f, which is by rank theorem, this is nothing but dimension of V. V in this case is k power n minus dimension of the image rank minus rank of f. If you call this rank to be R, then this is, and this dimension we know k power n as dimension n minus R. So, we know dimension of L0 is n minus R, where this R is the rank of f or rank of the linear system. That is how we have defined rank of a linear system. And then we have proved that the solution space of the E is nothing but this affine space x prime plus L0, where x prime is a special solution. In L, E is a special solution. You find somehow the special solution, and once you know one solution, then all other solutions are precisely the elements of L0 added to that special solution. So, therefore, this L of E is an affine subspace of k power n of dimension equal to dimension of L0, which is n minus r, where r is the rank of the system. So, this language affine spaces etc., we are planning to do it in a second course on geometric linear algebra. So, with this I want to end this section, and I would like to start now studying more precisely I want to start a new section called direct sums and projections. Direct sums already we have done something, but I will do it together with the projections. So, I will as I said that V k vector space and let ui I in I be a family of k subspaces. Of V. Then we have this product space ui and also the direct sum, which is a subspace of this product space. Note that though they are subspaces of V, this product is not a subset of V, and therefore this direct sum is not a subspace of V. So, there are some k vector spaces, but I still want to, because this is not an arbitrary family of vector spaces, this family of subspaces which came actually from V. So, there have to be some connection with the given vector space. So, this is what I want to do it more precisely. For example, we did already some similar thing in the example when I proved dimension formula, that I did it only for two subspaces, but now I want to carry on that study more precisely for arbitrary number of subspaces of V. So, as far as the vector space is concerned, I can consider a sum of ui's. This is a subspace of V, k subspace of V. In fact, it is the smallest k subspace containing all ui's, and I would like to relate these two. This is a direct sum and this is a sum. So, this is the sum space, and this one is a direct sum. So, a priori they are different, they are even as sets they are different, but I would like to relate them with a linear map, and obviously one can guess from the earlier remark that there is a natural map from the direct sum ui I in I to a sum. Remember, the elements of the sum space is precisely the finite sums of elements which are coming from each ui. So, this is we have seen this earlier, this is sums like summation ui, I in I, and only finitely many components are non-zero, that can be written simply as the tuple ui belongs to the direct sum. So, it is obvious the tuple ui in this direct sum as only finitely can be finitely many components are non-zero, that is mapped to their sum, and obviously we will study this map. What we have to do is we have to compute a kernel, we have to compute image, and so on and so on. So, this I will continue from next lecture, and then along with that a projection maps are some special endomorphisms of a vector space. So, all these concepts I will tie together nicely, so that these concepts will be very useful for the further use. Thank you.